Hi, welcome back my statics friends. In this video we are going to actually get into the computations of magnitudes of moments using scalar methods. We defined a moment in our last video as being a rotational effect on an object, and one of the two requirements that we'll need when we start calculating equilibrium or determining equilibrium. And so in this video I'm going to show you how to do the scalar method. So without further ado, let's get started. So in our previous video, we talked about different types of moments being, either a concentrated effect or a single force at an eccentricity, but we didn't really talk about the moments that these forces created. And so I want to kind of revisit that just a little bit in this video. In the picture that we have here, we're talking about moments of forces as opposed to the direct ones. And what I have here is I have a coordinate system that is x this way, y to the right, z up. Force there, and this diagram indicates a moment that is a positive moment about the z-axis, this particular one here. If we remember our right hand rule, if I take my hand and I kind of curl it in the direction of the moment, my thumb is pointing toward the positive z-axis, z direction, so that's how we know that that's a positive moment. Okay. On addition to that, I can also create a moment about the z-axis by putting a force here. Okay. In fact, this force Fx can cause a moment about the z-axis because it has a perpendicular distance to that z-axis measured by this, what I'm calling as a dy distance. So a force x, even though it's in the negative direction, will cause a moment, and this will also cause a positive moment, a positive dy, and a negative x direction force will cause a positive moment about the z as well. And if you think about it, it's like putting, holding this point still here, and this thing is wanting to wrap itself around that z-axis. Okay. In this particular case, that's the only moment that is produced. But if this force were drawn up here somewhere such that it wasn't acting at, at x equals 0, but was rather had an x equals, say if it was, 1 inch up or something, then it would produce that same moment about the z-axis, but it could also produce a moment about the y as well. Now, there is no eccentricity from the y-axis. That's why there is no y moment. It's just a pure z type of moment happening here. Likewise, if I come and I look at a different picture, and now I have that same rod, and now I take a force, and it's an Fz force with the same dy dimension. It's applied at the same location as the one that was here, but it's just in a different direction now. This positive Fz force will now cause what would be a positive moment about the x-axis. And again, this force has to be perpendicular to the distance from the axis, or I said that backwards. The distance has to be perpendicular when measured from here. So this point from here to the origin is some distance dy. This will cause a positive mx moment. So we've got to kind of come up with some relationships to be able to compute these. But and we'll work through some examples to hopefully illustrate it. This is kind of a tricky concept to wrap your head around as you're kind of playing with things a little bit. All right, so the way that we're going to do this, and the way that we're going to calculate the magnitude of a moment, we're going to use, there are two different formulas that you're going to see come across. The first one is for calculating the magnitude. Okay, and so it's just simply, and this may be the definition that you saw back in a basic physics class. Okay, and it's for calculating the scale. Remember, magnitudes are scalar quantities; they are not vectors. Okay, so the magnitude of this, which the other way of saying this, the way we had it would be the magnitude of an m naught vector. It's the same writing. Remember our notation here. Okay, but if it doesn't have a hat on it, it's not a vector, and I'm writing this as being without the absolute value brackets on it. Okay, that this is a force times a distance. So F is the force, and D is what we call the moment arm. Okay, now the requirement on that moment arm is that it must be perpendicular. It's a perpendicular distance to the force, and that was the case that we had in all the two pictures happening up above. Okay, now we also outlined kind of a right-hand rule for determining notation. I showed you that one, so that's what, kind of keep that in the back of your mind. You'll find in statics there are a lot of right-hand rules that come around. We've got the right-hand rule for the Cartesian coordinate system. That was this guy, x on the thumb, y 4 fingers, z is up. All those would be the positive directions. Now I can turn this any way as long as those stay perpendicular to each other. I can orient my axes however I want. Okay, but I need to do that in order to be able to make the cross product work, and you'll see that the cross product becomes one of the ways to calculate vector moments. Okay, and so that's one right-hand rule. The other right-hand rule we talked about was the double-headed arrow notation, in which I take, that we talked about earlier, that for the Z moment, my hands go in the direction of the curl, and my thumb is now pointing up when I do that, when we're looking at this picture up here. Okay, so that's the second right-hand rule we'd say. There will be another one that comes around a little bit later in the series as well. So just remember, right-hand rules are kind of the key to everything that we're doing. And part of that has to do with the math restrictions that we have. All right, so force times distance, that's what it's going to be. Now, just for reference right now, and we'll come back and visit this in a future video, that the vector formulation for a moment is a moment vector m naught, okay, is going to be equal to some r crossed into some f. Okay, and so if we kind of look at this, we can play with our cross product identity. Remember that the magnitude of a vector that is the cross product of two other vectors is the magnitude of the two components multiplied by the sine of theta. Right? Well, if I make theta here equal to 90 degrees, meaning that it's perpendicular, meaning that the r is perpendicular to the force, 90 degrees, I get force times distance. That's where the formula that we see up here is coming from. It's actually a vector equation that's been simplified with a restriction assumption on theta. Okay, so this is the more powerful of the two methods, and we'll do a lot with this. In fact, in three-dimensional, this is all you can do, because it's so tricky, and so it's just not convenient to try to do scalars with it. Now, in simple cases, we can make scalars work, and I'll show you an example where that's the case. But typically, the vectors are the way to go for three-dimensional problems. Okay, and so just kind of that's where we're headed with all of this. Okay, all right. So now if we kind of look, okay, here's that right-hand rule again that we have, and in particular for our vector. So if I have, our moment's axis, the axis of rotation, if you will, that's this vertical line that's here, and I have a moment m naught vector that's acting about that axis, then all I have to do is choose a point somewhere on the line as point O, okay, and then here's my force vector here, okay, and all I do is I take an r vector from this point to a point on the line of action of the force, which would be this line. And again, it doesn't have to be in the x, y, or z direction. It could be, in some three-dimensional line, if you will, that the r is from a point on the axis of rotation to a point somewhere on the force. Now, it could be up here, it could be down here. The mathematics will all work itself out. And that's one of the beauty of this r cross f method is that r does not have to be, when r is a vector, does not have to be perpendicular. The cross product operator, this determinant, will take care of the orthogonality and will make them, will give you the perpendicular pieces that you're looking for. So it's a lot easier, and it's you don't have to think quite as much about it. You just have to set it up. All right, and then so if our m naught vector is r crossed into f, then if you remember the 3x3 determinant, for each of these vectors, I, j, k vectors across the top. The second row is the first guy. This would be my a vector, if you will. And it's going to be his component. So we're going to take the rx dimension, the ry dimension, and the rz dimension for this particular force. And then for the f vector, it would be his fx component, his fy component, his fz component. That's how you calculate the moment vector. Now, at the end of this computation, I'm going to get something times I plus something times j plus something times k. It is a vector at this point. It's not just a scalar. Once I have the vector, I can find the scalar by doing Pythagorean theorem on the terms, just like we did with all the force vector stuff a couple of lessons ago. So that's kind of where we're going with all this. This is more powerful, but I'm going to show you, first off, we're going to do some of the scalar stuff and kind of get ourselves going here. And we'll revisit vectors in the next video. Okay, so let's take a look at a couple. So suppose I want to figure out what is the equivalent moment m naught for just a simple member that is 100 newtons, okay, that is located at a 0.2 meters from this point O, which could be a support reaction or something, but say at the support, the equivalent moment m naught of this force then is going to be the force multiplied by its perpendicular distance, and this one's pretty easy. The force is up and down, so the distance is horizontal. Okay, so m naught is going to then be 100 newtons times 2 meters is 200 newton meters. That would be the magnitude, and again, that's the magnitude of this guy, right? Okay, and so 200 newton meters, and then what we do have to keep track of, though, on this when we do scalar methods is the direction of the moment, right? Because if my 100 newton force were acting up, it would still have a magnitude of 2 times 100, but the direction would be completely different. So what we're going to do is we're going to hold this point still here, and I'm going to put my finger in the direction of the force pushing down, and so this is going to cause my moment to want to go this way. Okay, it's going to be a clockwise direction moment on this. So I'm going to write that as 200 newton meters, and then clockwise. Now, by our sign convention, I can also write it as minus 200 Newton meters, okay, would be and then I could put a, a clockwise kind of thing there. That's another way of writing it. We've got to be kind of careful on that, and this will kind of dictate the vectors, but normally I will just report this answer, 200 Newton meters, and I'll show an arrow so that there's no doubt which direction I think the moment is going. All right, so we're going to always indicate the direction as the note says here. All right, so let's try a different one. Let's calculate the same moment m naught. Now I have a bar that is 3 meters, okay, horizontal, and then it's down 0.75, and I have a 50 Newton force acting horizontal here. Okay, well in that case, the moment about O, all I'm going to do is I'm going to extend this line, okay, and remember, forces are sliding vectors. It means that I can move them anywhere I want on their line of action. So if I slid him all the way over to here, I now have a perpendicular distance that can be established between those 2 points. And it happens to be the same as the 0.75 meters here. So the moment m naught for this picture is going to be 50 newtons, horizontal force multiplied by 0.75 meters is the perpendicular distance, between this point and the line on which the force is acting. Okay, now notice the 3 meters dimension doesn't show up anywhere in the calculation, okay, because the force is horizontal. In order for 3 meters to show up, I'd have to have a vertical force, kind of like what we did up here. All right, so 15 newtons times 0.75 meters, that gets me 37.5. Now again, if the force is here and it's acting to the left and it's below the point, that's going to cause a rotation that's going this way, which is clockwise. And so that's why I write the answer as 37.5 Newton meters clockwise. All right, so let's try another one. Okay, let's take a beam now that is 4 meters tall, 2 meters over, and then has a little hang down that is 1 meter. Okay, well, we'll play the same game. Okay, and now all I have to do is look at this, and so this distance is 3 meters. All right, if it's 4 meters up and I come back 1 meter, it's 3 meters up from that point. So the perpendicular distance in this calculation then is going to be 3 meters, or I could write it as, what would be 7 kilonewtons times 4 meters all the way up to here, and then back 1 meter minus 1, there's the 3. Okay, so the 3 is there. So that becomes 21 kilonewton meters. Okay, now, the direction on this one, though, if I look, this force is now pushing to the left, and it's above my point. This guy is going counterclockwise. Okay, and so that would, by our sign convention, would be a positive moment for our calculations when we look at those. But that's how we can those are some of the things that we can do with some of the scalar quantities in this. All right, so I'm back. I found another 3-dimensional example that I figured we should include in our scalar computations as well. Okay, so we'll add this one onto it. So what I have now is, and it's a little bit more complex on this, is that we want to find then, say, the moment about different locations. Okay, so what I have is I have a moment that we're going to act on about our different axes that we want to find is mx, my, and mz. Okay, and I have a force vector that has components acting at this point A. Okay, so it's 200 newtons to the right in the positive y direction, it's 40 newtons in the negative x direction, and it's 10 newtons in the positive z direction. And each one of those is going to cause a moment about a particular axis. Okay, now this point is out in space. It's not over any of the axes. So point A can be said to be minus 3 meters from the origin. It can be positive 4 meters in the y direction, and it is positive 6 meters in the z direction will be our dimensions. So our a coordinate on this, if you look, is going to be minus 3 plus 4 plus 6 will get us our moment there. Okay, and these are all meter calculations on those. Now, if we look at these forces, each one of these forces will cause an effect about different axes. So we're going to take these things one at a time. Okay, so the first one we're going to look at is we're going to look for anything that causes a moment about the x-axis. So if I look at my forces, okay, remember we're looking for forces and perpendicular distances from x-axis. So if we look at the distances that are perpendicular from the x-axis, I have a 4 meter horizontal, and then I have a 6 meter vertical that looks like this. All right, so clearly what will happen is that for the x-axis, this 10 Newton guy acting up has a perpendicular distance of 4 meters from the x-axis. Now again, the x-axis is this entire line. It could be a point here, a point here, a point here, anywhere I want along those lines. If I move my force down, the distance on this back where this dotted line is also 4 meters. So we've kind of used this cube. It's almost like the parallelogram approach that we use for finding resultants. Okay, but we've set up this cube to kind of triangulate where this point is. Okay, and so if we look at the computation on that, then this is going to cause a 10 Newton times 4 meter moment, and this guy is going to cause us to want to wrap around the x-axis this way. So if I'm looking at the end of our axis, this would be a counterclockwise moment. And the way I know that is I put again, kind of putting my hand on the x-axis, and the 10 force is going up. It's wanting to curl the system this way. So again, your axis is down here at the palm of your hand. And so that's how I knew that that was going to be going in that particular direction. So if we're going in that direction on there, and I do my right hand rule, so we're doing this, you know, kind of got here, and I point this, my thumb is now pointing in the positive x direction when this thing tries to wrap around it. Okay, so that's a positive moment. So 10 newtons times 4 meters, positive quantity is the first term. Okay, now if I look, there's also a 6 meter dimension that's perpendicular to x. Okay, and for that I can take 20 newtons times 6 meters will also produce a moment about the x-axis. All right, and on this one, if we look at it and kind of do the same thing, now again, my palm is on the x-axis and my hand is wanting to go this way. This object is wanting to curl this way. Okay, and if I do that on there, my thumb is now pointed in the negative direction. And so this moment about the x-axis would then be a minus 20 times 6. So you got to watch the signs. That's the danger of the scalar method, is you got to watch the signs and put them on by hand specifically. So if I do that, that's 40 minus 120 is a minus 80 Newton meters. All right, so the negative moment on this thing tells me that my moment, my double-headed arrow would be acting, it would be acting up that way. Okay, along the x-axis where this is x. Okay, so that's what that guy is doing. And so you see that multiple forces can contribute to the same moment effect depending on their eccentricity. So we got to be very, very careful in what it is that we're trying to do. Okay, the my that is in here. Okay, so now let's see if we can figure out which ones go with the my moments. So these are the moments about the y-axis. Okay, and so if I do this, let's start with perpendicular distances to y. Well, there's a 3 meter perpendicular distance. Okay, so the force that we would use with this 3 meters would be the 10. Okay, so last time it was 10 times 4, now it's 10 times 3, gets me the moment about the y. And if we play the same game and I put my palm on y and this force is coming up, this is a positive y moment. Okay, as we're trying to look for that. So that's why it's 10 times 3 and it's a positive term in the first term. Okay, the other dimension that's perpendicular to y then is the 6. Okay, and so the one that is perpendicular to that guy that causes a moment about the y then will be this 40 Newton guy. Okay, and so if I look at it, and so that's 40 times 6 is the moment, and then the direction, again, palm on the axis, and my hand is trying to curl this way, my thumb is now pointed negative, like that, all right? Okay, and so if that's the case, that's why it's a minus. So it's 10 times 3 positive minus 40 times 6 negative. Okay, it's going to be a negative 210 Newton meters. All right, so that means that this guy in the y direction is going to have a double-headed vector that is looking something like that. Okay, where y positive is that way. It's the opposite direction because it's a negative sign. Okay, and so very quickly I can get the sense of what's happening to this object. All right, now the last one, kind of playing the same game. We're going to do the moment about the z-axis, and the perpendicular dimensions to z are going to be 4 meters, and then they're going to be what would be a 3 meter dimension on that one. All right, so the 4 meter, the one that causes a moment about the z-axis with the 4 meters is this guy. Okay, so again, it's horizontal, so I need a force that's perpendicular to that that's not in the z direction. It's got to be this x guy because the 4 meters is a y dimension. Okay, and then same kind of game as always. It's causing it to want to rotate that direction around the z-axis. My thumb is pointing up. That's why it's a positive. So it's 40 times 4 positive. Okay, and then the last one is we've got our 3 meter dimension, which is this one, and the moment, or the force that we're going to be looking at that causes that moment about the z-axis, okay, is going to be our 20 value. Okay, because again, this force, or these distances, and we're looking at any point on the z-axis, so I'm looking here, so that dimension is 3 meters. Okay, and so this 20 is going to be multiplied by 3. And again, force is going that way. My thumb is kind of acting down, and you kind of get the idea. I know it's a horrible visual trying to see that, but you got to kind of play with it and get a sense of which way your hand is wrapping about this, as we start to kind of look at it. So that's why it's 40 times 4, positive, minus 20 times 3, negative, gives you positive 100. So this guy, because he's positive, is actually a moment that's looking like that. So it's the net effect is it's trying to wrap that direction. Okay, and so that's how we can use the signs to help us tell directions. But you got to draw these very, very carefully, and you got to get the signs right by hand. That's the danger of the scalar method. All right. So anyway, so sorry about the premature ending there a couple minutes ago. This is a little bit more involved. So, okay, and so we're looking for scalar calculations that we're trying to do. Okay, you notice that in order to find moments, say about a line, say from O to A, I could do the moment about O, or I could do the moment, about any point on that line, that it would require a whole lot more effort, since the components are not perpendicular to our line. Because I chose the origin, though, I do have perpendicular dimensions, and it works out fairly well. But if you don't have a perpendicular ability to find that, then this becomes a whole lot more complex, and you're almost definitely forced to go back to R cross F, or the vector formulation. But this is how you would do a scalar in 3 dimensions. You got to be very careful because you're getting forces in all directions. You got to get the right dimensions lined up with it. So anyway, hope this has been clear. If you got any questions, leave us some comments down below. Otherwise, we will see you guys in the next video. Thanks. Remember to like and subscribe. Bye.